like to tell you about one of the recent and promising approaches for the point cloud matching task that has Lepard abbreviation. Lepard proposes a new approach for point cloud matching that can be applied to both rigid and deformable scenes. And point cloud matching methods often consist of two phases: point cloud feature extraction followed by the search in the feature space. And most of the feature extractors rely on 3D convolutional networks. Such features are translation invariant, but they may cause ambiguity in scenes with repetitive geometric patterns. So authors were motivated to eliminate such ambiguity, and they did that by enhancing features with some positional knowledge in 3D space. And probably that is one of the main contributions of this work, leading to superior results in both rigid and deformable cases. Let's formalize the problem which this paper solves. So given 2-point clouds, S and T, the task is to find a set of matches which can be used to recover the warp function. And we consider a match of points as a good match in case that Euclidean distance between warped point from S and the corresponding point from T is lower than a certain threshold. This is how the architecture of Lepard looks like. The baseline consists of 3 parts: a fully convolutional, feature extractor, KPFCN, and the proposed TMP layers, which include the concept of transformer with self and cross attention and the idea of differentiable matching. Local geometry feature extraction is the first step of Lepard. Authors use this KPFCN backbone, but with some custom changes in the decoder part. And here 2-point clouds are processed with this KPFCN, which outputs expected point clouds, downsampled point clouds, and extracted geometric features. Then goes relative 3D positional encoding. That is the main contribution of this work. The idea lies in applying a function to a point cloud. This function produces a positional encoding of a 3D point. And it also has a useful property, that is a dot product of 2 such positional encodings enhances the relative distance information between a pair of points. When positional and feature encodings are prepared, they are separately passed to the TMP layer, which include a transformer block with self and cross attention, a matching layer, and a soft procrustis layer in order to estimate the internal rigid transform. The first part of the TMP layer is the transformer. It takes the positional and feature encodings and processes them through the self and cross attention layers. The self attention layer is applied between the same point clouds, and its main intuition is to aggregate some global context. And the cross attention layer is applied to different point clouds in order to exchange information between these point clouds. So the transformer layer updates our geometric features with some more context information, like here. When feature vectors have been updated with more information, they are processed with the feature matching block. And here, positional and feature encodings are finally merged into the scoring matrix by using another two trainable matrices. Then the scoring matrix is transformed to the confidence matrix by applying the softmax function. And indices of the most confident cells represent point matches, which are further extracted with a threshold or with a number of matches. And the last one step of the TMP block is soft procrustes. And I would like to note that this is only the intermediate step, which is not the output of the network. The network is aimed at predicting only matches, not a rigid transform. So the purpose of this layer is to estimate the intermediate transform between point clouds. That is done in order to improve further search of matches. Rotation and translation are calculated here with some tricky formulas and SVD decomposition. And to be honest, I didn't really get the idea of them, so I can't explain them to you. But I can explain like why they calculate this intermediate transform. It is used for repositioning. Since the paper is aimed to find more matches in non-rigidly deformed scenes too, it is a good practice to align the point clouds with some rigid transform after the first iteration of search. And after aligning the source point cloud, the positional encodings are also updated. And it helps to fix some incorrect knowledge about relative distance information between not yet unaligned point clouds. This, as authors said, improves the effectiveness of the cross attention and hence further matching. And finally, that's it. After such a point cloud repositioning, the second TMP layer predicts the final matches. Let's make it clear about what is supervised here. So they use two losses, matching clause to train the confidence map from the matching layer, and the warping clause to train the rigid transform estimation in this procrustes layer. And you may probably think that we need both the GT for matches and GT for the warping function, but in practice, the only GT you need is a warping function. The GT of matches are collected by warping a point cloud and searching nearest neighbors for matches. And since the TMP block is repeated 2 times, the total loss is constructed with the matching and warping losses repeated as well. And before moving on to evaluation, I would like to mention another contribution of Lepard. That is a new benchmark for partial point cloud matching. And its distinction is lies in containing a point clouds that are non-rigidly transformed across the time axis. And the figure here shows an example of point cloud pairs with different overlap ratios. And the figure below is a histogram of the overlap ratio. Based on it, authors also separated their benchmark into two versions, containing point clouds with lower and higher overlap ratios. Here are some evaluation results for the 3D benchmark containing rigidly transformed point clouds. And authors compared the quality of both matching and registration with found matchings. And for rigid cases, it a bit outperforms Predator. For 4D cases, Lepard made a lot more improvements in feature matching, and it strongly outperformed other methods. You also may observe visualizations when two non-rigidly deformed scenes are aligned with non-rigid ICP plus matches found with Lepard. And it does it much better than Predator. Probably I should mention some limitations too. First is that matching and registration in low overlapping cases is still a challenge. And second is that in deformable cases, Lepard doesn't explicitly handle topological changes. Conclusions. To be brief, the main contribution of this work is the usage of positional knowledge with a function which gives an ability to extract relative distance information through the dot product of these encodings. And by leveraging this positional knowledge, Lepard demonstrates state-of-the-art feature matching results for both rigid and deformable scenes. Thank you for your attention.